I'm so delighted to welcome you here to this inaugural lecture. My name is Anthony Bull. I'm head of the Department of Bioengineering, and occasions like this are just so fantastic. They give us great pride, great encouragement, and I just first of all like to specifically welcome Manos's family here. So I'm going to pronounce the names pretty well: Georgia, Pavlina, and Arni. How's that? Okay, not too bad. Also, his former students and group members, some of whom have travelled a little way to be here. It's a great pleasure to welcome you back to Imperial College. This is a family occasion. It's Manos's family occasion. It's also a family occasion for the Department of Bioengineering. It's a family occasion for the community of Imperial College. And it's for us to celebrate and acknowledge one of us, one of our own, who has achieved this prestigious title of professor. And has recognition as a research leader in his field of endeavour. Manos is a long-standing Imperial member. He came here in 1996, I understand, quite a long time ago, for his PhD studies, following his undergraduate and his first postgraduate degree in Greece, and some military service in between, I think. He secured a postdoc in electrical engineering, where he did his PhD, and then came over to bioengineering in 2001 as a lecturer. And boy, are we delighted that he did so. It was a time when the department was very small. I think he was about the 8th or 9th member of academic staff, and has been a stalwart of our department ever since. Universities are about creating knowledge, communicating knowledge, and securing the translation of that knowledge for societal benefit. And I think we will hear tonight in Manos's lecture how he has been achieving those three things in a significant way. He excels in all of these. He's a great teacher and is the proud recipient of one of our Bioengineering of the Year, Bioengineering Lecturer of the Year awards in the department. His research is creative, has great technical depth, and is recognised internationally in many ways. And I just want to point out that a thread that runs throughout Manos's career and life, I understand, is his broader contribution. So even in his research, he contributes extensively to leadership through, for example, his extensive editorial work in the field, an important activity in his research area. And he's committed to his work achieving societal benefit, and I hope that today we will hear a little bit about that, including, for example, his cochlear implant processor work. But what I'd like to finally mention before Manos comes up is to emphasize and acknowledge his great contribution to the growth and success of the Department of Bioengineering at Imperial College, and hence the discipline of bioengineering. To many of you, it may seem that bioengineering is this wonderful, fantastic, brilliant, large activity, this brilliant department. Well, I would contend that it probably has always been brilliant, but we were small and we struggled and we had lots of issues to deal with in the early days. And I can assure you that this success is delivered through the hard work of a few key individuals who've gone over the call of duty, over and above the call of duty over many years. And Manos, we want to thank you specifically for this. Manos has done many things in the department that have contributed to us achieving what we are today. He's held many key departmental roles, including, for example, admissions tutor and now senior tutor, a role that he fulfills fantastically well for the benefit of all our students. And he gives great support not only to them but to the staff as well. Manos, we are desperately proud of your achievements. We're delighted to call you colleague and friend, and we look forward to your inaugural lecture.
I would like to thank Anthony for the very generous introduction, I would say. And I would like to thank each and every one of you for being here tonight. I will share with you some of my research endeavors and some of our research achievements. So given that the composition of the audience is a bit wider, that is to say, I understand that there are many people who might be from life sciences and medicine, so we will start actually with the transistor. We will start with the transistor technology, how it developed and how its development actually contributed to the conception of the log domain circuit paradigm, which has defined me to a certain extent academically. I will explain to you how log domain was conceived and how we progressed the field and how this progress actually has practical advantages. Following that, I'm going to go in two directions. I'm going to show you examples of high-performance linear time invariant circuits that are suitable for biomimetic cochlear implant processors and for bionic ear processors. And I will continue by actually showing to you progress that we have made in an emerging field, the field of cytomimetic circuits. Naturally, I will close with acknowledgements. So, the transistor. Do you know when the first transistor action was observed? You thought that you would be asking the question, but I am asking the question. It was the 16th of December, 1947. So in 10 days from now, it will be exactly 70 years, 70 complete years that the transistor was invented. And you can see here, this is the team that invented that. Brattain, the experimentalist, he was the one to observe the first transistor action. Bardeen, a brilliant theoretician, he went on, actually, testimony to his brilliance is that he went on and received a second Nobel Prize in 1972 for his work on hyperconductivity. It's the Bardeen-Cooper-Schrieffer BCS theory. And then here you can see Shockley, another legendary figure in the field of microelectronics. He was the boss of the other two. What you see here is the first point contact germanium transistor. This range is in the order of centimeters. And what you actually see here is a little amplifier circuit, because they were after building more reliable amplifiers for telephony circuits. This was at Bell Labs. So they won the Nobel Prize in Physics in 1956. The next milestone in the development of microelectronics was actually the realization of integrated technology back in 1958, 1959. It is Jack Kilby from Texas Instruments and Robert Noyce, who went on actually to co-found Intel, that are considered to be the fathers of integrated technology in microelectronics. You can see here the first integrated chip and some of the sketches of Jack Kilby. Nowadays, of course, microelectronics have progressed. You start with a slice of crystal silicon there, carefully prepared. We call that wafer. And then through a process that involves light, the process of lithography, we succeed in transferring patterns onto the wafer. And in this way, we manage to create very small transistors, resistors, and capacitors on a very small chip area. And in this way, we can create the chips. So, of course, there are other physical and chemical steps. And once this particular process has finished, then if you want to take one of those circuits there, the chip, you actually have to take the chip from the wafer. So that's why we call chips chips, for those of you that you might not be aware. Once transistors became integrated, they started becoming smaller. So, and we started actually having more and more transistors on a piece of silicon. So when I was born around 1970s, we had a few thousand transistors per chip. Now we have hundreds of millions and billions of transistors. This progress followed Gordon Moore's law. Gordon Moore was to be one of the co-founders of Intel as well, who in 1965 expressed for the first time what is now known as Moore's law. And he actually said that the number of transistors that we can put on a square inch with minimal cost would double every year. And then later this law was re-expressed, re-articulated, that the doubling would be taking place every 2 years and so on. This is the particular sketch that he used in that seminal paper of 1965. Back then, he looked at the previous 5 or 6 generations of technology, and he came up with this particular observation, which now has become Moore's law as far as how the transistors are getting smaller. For those of you who are not from a technical background, how small and how cheap have transistors become? Well, if the initial integrated transistors were as big as a car, then the transistors we have today are as small as an ant. And conversely, if now every one of you have microprocessors in your smartphones, right? If you wanted to realize that processor with 1970s technology, you would need as much space as the space that you would need to park your car. And if actually the house prices fell at the rate at which transistor price fell, with one candy you could buy a house. This is how much progress has been made. So transistors are becoming smaller, faster, cheaper, from mainframe computers to personal computers, laptops, millimeter scale computing, and size goes down. Now we are at the range of a few nanometers as far as how big are the transistors. For those of you who are not from technical background, 1 nanometer is you take 1 meter, you divide it by 1 billion, and you take 1. Or you take 1 millimeter, you divide it 1 million times, and you take 1. This is how much is 1 nanometer, right? Clearly, such miniaturization of the transistor means that other areas of technology are actually benefiting. Given that we are the Department of Bioengineering, it would be useful to take an example, the pacemaker, and see how it has developed over time and how the transistor development has influenced this. So from the early electrocardiographer of Eindhoven, who went on actually to win a Nobel Prize in 1924, you can see it here. In 1957, 58, 59, in that period after the invention of the transistor, you can see here Bacon's circuit. Bacon is one of the founders of Medtronic. So that particular circuit, and you can see here the little transistors, was used for actually realizing the first wearable cardiac pacemakers. And later it was Great Batch. You can see him here with another of his famous circuits that was used, that circuit, for one of the first implantable cardiac pacemakers. And these days we are at the stage that we have fully implantable cardiac pacemakers. And we have now many types of devices that are wireless, implantable, including deep brain stimulators, gastric stimulators, insulin pumps. Of course, we have also retinal implants and cochlear implants that I'm going to be talking to you about a bit later. Now, as the transistors were getting smaller, and because when you have a smaller transistor and these are faster and cheaper, then the performance over cost ratio actually means that if you go for a new generation of technology, then you will benefit. Why? Because the new generation will create better performance. You will get a bigger market share, which will bring profits, which if you invest it into a new generation of technology, would feed back and actually give you the competitive advantage. However, whereas up to a certain point we kept on making the transistor smaller and smaller and we kept the operating voltage the same, then after a certain point, which is that point when transistors became around half a micrometer big. Half a micrometer is you take 1 millimeter, you chop it down 1,000 times, you take one, you take half of that, and that's half a micrometer. So up to that point, actually, we used what we call constant voltage scaling. There was no practical benefit after that, and then we used what we call constant electric field scaling, Dennard transistor scaling, because Dennard in 1974 published one another seminal paper there. So in this type of scaling, all the geometrical dimensions of the transistor become small, but in such a way so that the fields inside the device remain unaltered, and which crucially means that as the transistor becomes smaller, the voltage becomes also smaller. So power supply was going down. So what, one might ask? Indeed, I will explain. As the transistor becomes smaller, so as you go to the right here on the x-axis, the transistor becomes smaller, that is to say time progresses in this way, then the operating voltage was going down, which meant that somewhere here, some of the techniques that we, continuous time, continuous value, analog designers, some of the techniques that we use become challenged by this lower voltage level. So one of the central problems that we have in microelectronics, and we had to deal with that under this lowering voltage, is how we are going actually to build a linear time invariant system. So the voltages are getting lower. We have this very central problem. We are analog designers, and somehow we need to make sure that we can design this by accommodating ourselves within that reduced voltage level. Typically, in a conventional design pathway, you would start from a nonlinear device. You would combine many of those, squeeze them, stretch them, do several things onto them to create a linear block. Once you have created a linear block, then you are going to start realizing physical connections in accordance with this state space. For those of you from non-technical background, state space is the mathematical description, the mathematical codification of the final system that you want to realize in the very end. So you want to realize something linear, so you need linear blocks. This is the conventional design philosophy. But as we said, this particular now step is challenged under this reduced voltage environment. So researchers and industrialists actually started thinking of unconventional design philosophies, which actually suit me very well. I don't know why. So could we actually do without the linearization step? Could we go directly from the nonlinear device to the linear time invariant realization of the system? That was an intellectual problem. What would happen? Would we benefit if we actually did that? Yes, we would benefit. Why? Because we would use our devices to operate in accordance with their large signal characteristics. So we would have high dynamic range designs. However, we would also spend power more efficiently. Why? Because we wouldn't actually spend power for linearization. Whereas before we need to combine many transistors, more transistors need more biasing, more breathing, more space, so we save power from there. And if this device happens to be one weakly inverted MOS, then you realize ultra-low power systems. So everything is good, right? No. There is no free lunch. So actually, mathematics become much more complicated if you want to realize this particular type of design philosophy. And it is this particular problem that planted the seeds of what was to become, and now it is, log domain. I'll try and explain that by means of a sketch. Let us say that this blue line here is the high power supply level. And let us say that we had before that this red line is the reduced voltage level within which now we have to accommodate the operation of our circuits. If you look at a typical exponential device there, you are going to see that large currents correspond to small logarithmically compressed variations of voltage there. So this is a large current, and this is a small voltage. So what if actually the information that we are interested in was carried by the current? Then we could always draw that current from the reduced voltage. The voltage is down, but I can always draw some current from there. And if I do that, then all this information that was carried by the current is now hidden within a compressed, logarithmically compressed voltage. Is this practical? Can we do that? Yes, actually, if you take one device and you diode connect it, a special type of connection, then you can always have your information logarithmically compressed there as a voltage, which is good. It's one way of dealing with the low power supply level, which, however, means that now all the remaining of your processing will be in the logarithmic domain. All of that will be in the logarithmic domain. And if you want, and we do want in the end to have, in this particular case, a linear response, at some point, you would need actually to exponentiate exponentially, to expand exponentially one of the internal voltages and have your linear signal here. So somewhere in there, in the processing in the log domain, what you have is a choreography between compression, expansion of voltages in such a way so that in the end you get a linear response. It has been shown that when we do that, we actually have better power efficiency than with the linear approach. And because we compress, expand, we compand, as we say, and we compand instantaneously. So this is the concept of instantaneous companding, which means that you start from a high dynamic range. This is the large signal. You compress it. You do everything in the log domain, and then at some point you expand. These were the key initial ideas. The initial contributions to such circuits were from Adams back in 1979 and from Siving in 1990. And you can see here some compression of the current through a diode, but it was a bit impractical, too many op-amps, discrete components, and so on. Here, this is actually a differential input, differential output linear integrator that was exploiting companding, but it was a first order system. We hadn't actually solved the general case, which is this one, and this is where Professor Douglas Frey comes to play. And he is the one who actually first suggested the systematic realization of high order log domain circuits. What did he do? We haven't solved the general problem yet, right? He actually did something brilliant, bold, and beautiful. He started from the linear state space and applied an exponential mapping. Why would you destroy a linear state space, one might say? Having done that, however, then at the top level, it was possible to have direct physical linearization of the final system. That was a masterstroke, by far a masterstroke. And it is this work now that we have progressed, as I'm going to be showing to you. To see quickly what this means, you start from a state space, you apply an exponential mapping on the state variables, then you end up with a much more complicated, to the first instance, expression of the different equations. But an experienced eye would see that you are actually, we can identify capacitor currents, and we can identify currents that go in and out of the capacitors that are directly realizable by combinations of large signal devices. So it is without linearization. And once you take all those blocks and you put them as Legos next to each other in accordance with the equations, you actually end up with your log domain structure. The log domain structure emerges. This is a top-down approach. So you start from a mathematical description and you end up with a topology in the end, the typical one seen here, where you have the logarithm of the input and the expansion of the output. Now, these particular type of circuits are not like the other ones. By far, they are not like the other ones. So if you have a sinusoid at the input, a sinusoidal signal, In most circuits, take for example an op-amp that has negative feedback, and you apply a sinusoid and you check the internal nodes. You are going to see there that all are going to be variations of this sinusoid. But actually here, the internal signals are completely nonlinear. They are choreographed in such a way so that input-output you get the linearity. And we need actually to have those signals nonlinear for the simple reason that we want to take advantage of the large signal characteristic and not have linearization. So this is what we mean by internally nonlinear, externally linear circuits. It was at that moment, at that time, that a much younger, thinner version of the speaker joined, had actually the honor actually of joining Imperial. And I remember talking with my supervisor, Alison Payne, and saying, you know, I was romantic. I'm still romantic. Give me something that is going to be challenging. And we started looking, and I remember actually Alison telling me, you know, Manos, everyone in the community expects for the next papers of Frey so that we understand what is going on. Nobody knew what is going on, why those things are actually operating the way they operate. So I started looking at high-order structures like this one. This is a fifth-order Chebyshev structure from Gordon Roberts, who realized, another key player in log domain, who actually realized this by variations of Frey's method based on signal flow graph. If you look carefully, and now I'm looking at these topologies, then you can interpret them as an interconnection of Frey's Lego blocks, which are actually interconnected in such a way so that they push and pull the correct currents into the capacitors. However, you can look at the same topology like that. You can identify different loops. We call them those loops translinear loops because they are a special type of loops formed only by capacitors, and their behavior is codified by equations of products of currents. I was not the only one who had seen that. Others had seen that, but most, they started looking and they were actually doing calculations based on voltages inside this particular circuit. Now there is a critical point. You start with a state space, a mathematical description, and you end up with something that has translinear loops, but you only see them when you synthesize that. You don't see it from the beginning. But if you actually have it in the end, shouldn't there be some synthesis method that could actually take into consideration these loops and start building this and going from the bottom up? And because those loops, we know that they can do nonlinear processing as well, it should be opening a window to nonlinear processing. This is how we were thinking. And coming from physics, we always liked the analysis. And what we actually did, contrary to other researchers in the field, we started looking at the currents that are fed in and out of these capacitors. And we made the crucial observation back then, that actually if you look at the differential equation of all these currents, you will end up, if you combine an exponential device like a Mosin-Wick inverter or a BJT with a capacitor, you will always end up with a differential equation of the current, the drain current, or the collector current, or variations of this. You will always end up with the dynamics of Bernoulli equation. I was pretty sure that somebody must have seen that. They hadn't seen that. And actually, it was clear back then, at least to me, that we could do many things with that. And this was, is this a discovery? I wouldn't call it a discovery, but it is a very useful observation. Why? Because actually the capacitors and the transistors are the bread and butter of electronics. And you tell them what the dynamic behavior of the current of that capacitor is going to be, no matter what. So it was important. And crucially as well, this particular differential equation can be expressed either in linear or nonlinear form. So it is a window to either linear realizations, cochlear implants, or to nonlinear realizations. We term it the Bernoulli cell because actually it was posed by Jacob Bernoulli back in 1695. So 1695 is a very fruitful period for the science in Europe. It's a few years after the publication of the infinitesimal calculus of Leibniz and a few years after the publication of Principia by Newton. And this is Jacob Bernoulli. He posed the equation, but actually the Bernoullis were a family of mathematicians that spanned for more than 100 years between 1650s and 1750s. They were a family of mathematicians. Johann, the brother of Jacob, had actually Jacob as his advisor, and he was himself advisor to Euler and de L'Hopital. And Leibniz was also corresponding with Jacob. And if you look at the sources, it is these three. So Jacob posed the equation, but actually it was those three that independently, they all seem to have contributed to the solution and so on. Somewhere around here, there is in the audience somebody who is doing fluids, hydrodynamics. So they go, what about my Bernoulli? There must be another Bernoulli there. Yes. That's Daniel Bernoulli, son of Johann, the hydrodynamics Bernoulli. And actually, they went and competed for a prize, the father and son. They both won the prize. They shared the prize, but the father was not very happy. You can check the source. Now, if you start now with the cells that we have identified, you put them in cascade. Variations of the previous one are conveyed to the next one. And crucially, you make two different modifications. So you start by the dynamics we have identified. You logarithmically drive the first one. But crucially, we left the U and V currents that go in and out of the capacitors undetermined. That was one contribution. The second contribution was actually the identification of new variables. Those variables were now ratios of products of currents. So we could see from here that we could have more rich realizations of the final logarithmic high performance topologies. When these U and V currents are time invariant, then you can have a linear state space. But if you make those U and V currents dependent upon other internal variables that you have identified, then you can create nonlinear responses in a systematic way. And to cut a long story short, going back to our problem, which was a basic one, how we are going to process signals in the log domain under a reduced voltage environment, how did I deal with it? Well, I started from the nonlinear device. This is a bottom-up approach. I skipped, of course, linearization. I identified a new set of dynamics, the log domain state space, which when you pair and compare with the target state space, you can realize whatever linear time invariant response you want. But crucially, we opened a window now to the systematic linearization of nonlinear dynamics, which was not there before. With this in mind, I hope I have put across to you how technology and log domain actually were going hand in hand and how the synthesis methods were actually being developed. What I'm going to show to you now in part 2 is I'm going to show to you high performance examples for cochlear implant circuits as an example of high performance linear time invariant systems. And in part 3, I'm going to show to you progress in cytomimetic circuits, which has to do with the systematic synthesis of nonlinear biomolecular and cellular dynamics. That's what I'm going to be showing to you in part 2, high performance linear time invariant cochlear implant and bionic ear circuits. Why did we focus on cochlear implants? For a few reasons. So, first of all, many people are affected by profound deafness and which is treatable only by cochlear implants. Secondly, there is room to be covered. There are improvements to be done as far as the performance of cochlear implant in the presence of noise is concerned. And thirdly, in our community, there is an effort to actually realize totally implantable cochleas. And looking at excellent previous works, we felt that we could progress that field and actually ultimately help society. I don't know if you have seen the reaction. Can we hear that? The cochlear implant has just switched on.
This is so good.
Could we turn up the volume?
Funny. It sounds a lot like. Oh my god, okay. It doesn't sound funny at all.
Doesn't sound funny at all.
It doesn't sound funny at all. It doesn't. No, okay. It doesn't sound funny. It sounds good. It sounds good. It sounds good.
So it sounds good, which is actually further motivation for us to try and improve this particular type of piece of technology. In order to understand our efforts there, we need to say a couple of things about the ear. So what we have in our inner ear is a cochlea-shaped structure, bony structure, which is filled with fluid. And along the length of this structure, there is what we call the basilar membrane. The basilar membrane is a physical membrane whose physical properties change in such a way so that frequencies, sounds of different frequencies vibrate different parts of the basilar membrane. So basically what we have in our ear is a miniaturized spectrum analyzer, effectively. And the way this works, just to put things across, when we take the cochlea, we unroll it. Low frequency sounds on one end. Higher frequency sounds on different parts. I think you get the idea there. If you now take the cross-section of the cochlea, then you are going to identify on top of the basilar membrane, you are going to identify little organelles there, the organ of Corti, where we can identify the inner hair cells and the outer hair cells. What the inner hair cells we see here do is that they actually detect sound, they detect motion of fluid, and through that they detect sound, and they actually encode together with the spiral ganglion neurons information about the sound in the form of neural impulses that go up to the auditory centers of the brain. On top, however, apart from the inner hair cells, we have the outer hair cells, which play the role of gain controllers. When a bomb explodes, knock wood, a bomb explodes next to you, you don't need amplification. You need amplification only when the sound is weak and soft. So what the outer hair cells are doing is to make sure that when sounds are strong, then effectively the gain goes down, as we can see from the physiological data of Ruggero here. So we have something that is tuned to a specific frequency. The basilar membrane has tonotopic organization, that is to say, we actually cover the audio spectrum by having logarithmically spaced the frequencies. And on top, we have detection and gain control. This is the analysis in engineering terms. Now, what happens with the cochlear implants? Cochlear implants are those types of implants that try to bridge the gap that exists in the auditory pathway when the hair cells cannot send the nerve impulses up to the brain, and we cannot detect sound. How do they do it? They have actually two parts, an internal part, the implanted one, which is surgically implanted and actually has a microelectrode array going through to the cochlea, where we will finally stimulate. And the external part actually picks up the sound, processes and codes the sound by means of a processor, and then the coded speech, if you want, goes through a transcutaneous telemetry link to the imparted part, where the spikes, electrical pulses are generated, which go down the microelectrode array, which stimulates the cochlea, which in turn elicits a response from the auditory nerves. And in this way, we manage actually to close the gap that exists in the auditory pathway. However, you can see down here the electronics of this, and they are pretty complicated. This is the internal part with the implanted part with the electrode array. This is the transcutaneous link electronics, and this is the external part. And in our community, there is a drive to make this part of the implanted, to have totally implantable cochleas. Why would you need that? Because that would boost the confidence of CI users. It would relax actually the constraints as far as their everyday life is concerned. And there are also some technical advantages, particularly with respect to the transcutaneous link that is there. So our effort and the effort of other excellent colleagues in the community has been to make this totally implantable. How would we need to go about that? Well, you have to actually model a segment of the basilar membrane, and we wanted to model that in a biomimetic way. We did that but by actually realizing 1-0 gamma-tone filters, and we collaborated there with Dick Lyon, a legendary figure in the auditory community, and I invite actually the students to go and check his website and marvel at the different contributions in different fields. He is here with his new book. So if we actually manage to mimic a segment of the cochlear membrane, then if we have a few of them, we could have a cochlear implant. If we have many of them, then we could start talking about bionic ear processors. The 1-0 gamma-tone filters can be viewed as a short cascade of second-order responses, bandpass and 3 low-pass, which, because we are after realizing a system like the ear that has 120 dB dynamic range, means that actually logarithmic circuits are very good candidate for progressing the field, for making a difference there as far as performance is concerned. So we went and implemented this with log domain. However, for the 1-0 gamma-tone filter response, we went with that because of 3 basic characteristics. We can control where the center frequency is, and we can control that electronically. We can control the gain with another single parameter. For those of you from technical background, you understand that you don't want to change 10 different parameters to achieve one thing. You would prefer simplicity. Simplicity leads to robustness. And we had another parameter that could control the tail of this response. And all of that, when you compare it with physiological responses, we were trying to mimic with electronics the physiological responses. If you actually compare now this particular filter against many other auditory filters and against a list of desired characteristics, you are going to see that they are one of the best. And on top, we could implement that with ultra-low power log domain techniques and go to the next step as far as technology progression for cochlear implants is concerned. So we mimicked, and we wanted to control the gain. We realized the chip, 124 dB dynamic range. We matched the auditory range, 3.4 microwatts consumption. How much is 1 microwatt? You understand? A 100-watt bulb can power up 100 million circuits that consume 1 microwatt. This is how small a microwatt is. We tested. Some people in the audience will identify this video. And what you are going to see here is actually the automatic gain response. So here we have a very strong signal and we don't have a lot of gain. And now gradually we make the signal smaller and smaller, and the gain should be increasing automatically. We are trying to mimic the physiological response of the cochlea here. This one. Now you are going to see the last smallest signal there. The response becomes very narrow, high gain. And now we are going to put the initial signal, which was strong, and you are going to see the gain automatically adjusting to something much, much smaller. We confirmed that we had done a very good job mimicking the segment of the cochlear implant. We confirmed tunability. We confirmed linearity. And crucially, and you are not going to find many results like these ones, we actually confirmed inter-chip variability, which meant that the circuit was robust. It would make sense to actually fabricate that. It was not 1 out of 20 chips that worked. So we were ready. We were ready then to put all the biomimetic channels next to each other and actually build our cochlear processor. No. Then we had to face a bigger challenge, and the challenge is the following. If you imagine that you have 2 channels, one corresponding to one frequency that is strong, then your automatic gain control is not going to amplify that. But if you have another one close to this that is weak, your automatic gain control will amplify that. So what you are actually doing, you are losing spectral contrast there. And because you are losing spectral contrast, you are losing intelligibility. And when we talk about cochlear implants, we want the spectral contrast for cochlear implant users to be at least 6 to 8 dBs higher than normal hearing people. So we had to face another challenge there, perhaps a more difficult one than the previous one. Everything here is now in the log domain. Now, if you want to control the gain of the center channel, you look at the output of this particular channel. Fine. But that does not lead to good performance when you put all the channels together. So what did we do? We actually applied bio-inspired engineering. And I know that the word bio-inspired is a buzzword, but we did actually apply bio-inspired engineering. So what did we do? We listened to the next few channels, and we listened to the other few channels on the left and on the right. And we took information from those channels and we controlled the gain in such a way so that the spectral contrast was not lost. That's lateral inhibition that you can have in many natural systems, including in the auditory system. And one might say, but I do that. I have the MATLAB code. I can do that. Yes, but this is not MATLAB code. This is actually pieces of silicon, very large scale integration, and you force the transistors there to do what you want in real time with ultra low power. Not an easy task. So we listened to the channels adjacent. We controlled the gain of the center channel by listening to that. And as you can see here, when the AGC coupling is off, your initial spectrum, dotted lines, the dashed lines, the initial spectrum, continuous line, the flattened spectrum, with bold line when the coupling is on, you can see the formants, the basic frequencies of the speech emerging. We tested that with psychophysical experiments. We had full approval. We used students from bioengineering. Normal hearing native persons we used. And this particular acoustic simulator of the cochlear implant was flexible enough, and what we could do is to corrupt speech with noise. And we made the speech as strong as the input noise was there. So we performed the experiments, and we had a 31 percentage points increase in terms of intelligibility across the different SNRs that we used. This is one of the very good figures that you are going to find out in the literature, and I'm being modest here. So this is how it looks an initial spectrum. This is the flattened one, and this is what happens when the formants emerge. And now all these experiments were performed in anechoic chambers. So I'll try and play this, and may I ask the AV team to actually increase the volume a bit? Can we do that? So listen to the initial speech.
Ready arrow, go to blue 7 now. Ready arrow, go to blue 7 now.
Right? This is what we get. when you do not have the coupling. This is what you get. Can you see the speech emerging, although the AV is not the best? So it worked. We went ahead. We realized that. We fabricated that. And this was our second chip, almost 100 dBs of dynamic range between 90 and 100. A few microwatts of power consumed, 6 microwatts per channel. It is acknowledged now from international reviewers as being part of the state of art, if not the state of art here. And what you can see here is tuning with many, with inter-chip variability. We confirmed with multi-tone experiments that we actually, yes, we could see spectral contrast happening with a few microwatts of power. And we are now at the stage where we optimize this particular processor. And we can optimize it in many different ways. I'm not going to go into the detail. And we want to attach after that a very clever stimulator there. We are working on this. And together with colleagues, I can see them here, Professors Stokes and Morse from Warwick, we would like actually to be able to pioneer a new high-performance, ultra-low power, and may I say, lower cost implant for the wider society. If you compare with previous attempts, you can see that we did a pretty good job. We almost doubled the dynamic range of the initial attempts, and we now have biomimicry, automatic gain control per channel, and spectral enhancement. And I can tell you that we have also confirmed across chips that these things work. Everything done in log domain. You wouldn't be able to get this performance in dynamic range if you didn't go log domain. What you see here with blue and green is previous attempts, and what you see with red and purple is our responses for low and high gains, all normalized to the center frequency. So based on the identification of those dynamics, we managed, that I showed to you, our contribution there, we managed to actually increase the performance of cochlear implant channels, and we are now at the forefront. And we are following now the next step, which is to integrate everything into a totally implantable cochlea, where everything is going to have been tested a priori. I'm now going into the third part of the talk, the last part of the talk, and I'm going to show you examples of how the dynamics we have identified can actually realize nonlinear, ultra-low power cytomimetic responses by means of log domain circuits. I simply want to stress that we are talking about an emerging field here. Across both sides of the Atlantic, there are groups that are working on this. It is a new field, and for us, it has been primarily a feasibility exercise. Can we do that? And can we do that in ultra-low power? And how are we going to do that? So I simply need to tell in advance that there is a tradition in electronics as far as using electronics to model biology. So the initial seed of what we call nowadays neuromorphic paradigm was planted by Carver Mead back in the late 80s, and in 1990 he had his seminal paper on neuromorphic electronic systems. What Carver had seen was actually that there were analogies between the operation of transistors and the operation of neurons. And today, 30 years after, we have silicon neurons, silicon synapses that operate in an asynchronous mode, that they operate in an asynchronous mode. They exhibit adaptability, and they try to mimic neural systems. We use now, very clever circuits, ultra low power, very low, very good power efficiency as well to process audio and video data, basically. Did we do any contribution to that field? That would be another inaugural lecture. So I simply want to say two key contributions, that the dynamics that you have seen, together with colleagues that are in other universities, we were the first to show that our dynamics there could represent the Nobel Prize winning Hodgkin-Huxley dynamics. That's one. And we recently have shown, together with Kostas there, that actually all the silicon synapses that you see there in log domain, they comply with the dynamics that I have shown to you, but all of them. However, we have recently started looking at the realization of cellular and molecular nonlinear chemical dynamics, as I said, across both sides of the Atlantic. There is a lot of activity out there that does with the development of physiological models specific to diseases, specific to organisms, specific to pathophysiology, specific to systems, different scales of models, and so on. You can have, recently, you could have dynamic models for brain energy metabolism, even for bone remodeling. You can see here, these are 34 different differential equations, something similar there, and so on. An experienced eye can see that in principle, it should be possible to realize them in ultra low power. Why would you need to do that? Because if you can imagine a processor that is actually reconfigurable, and you can have many of these, then you can set up your processor, you can configure everything in such a way so that you test different parameters, different variations of the model. And this actually shortens the development cycle for the bioresearcher and actually shortens the learning curve for bioresearcher. It's not the only one, but I'm just mentioning this to you. So in terms, for us, it was a feasibility exercise. Can we do this? Nobody had tried that. It's only a few groups across the Atlantic who are trying something similar. So at the start, we went about simulating. And what we did was we successfully simulated glycolytic oscillations. We successfully simulated calcium-induced calcium release intracellular oscillations, intracellular calcium oscillations. We also managed to successfully simulate the kallikrein activity model for atopic dermatitis, a model which is pioneered by Dr. Tanaka in our department. So we also managed to simulate the Chen-Ihara gene protein regulation network and so on. So we were happy that it was going okay, but we wanted to see whether actually we would be able to implement something that was at the forefront of research. So what we actually did was to focus on systems that mattered. One of these systems is the mammalian cell cycle. This is a cellular rhythm which is responsible for cell division, with the final stage being mitosis. And actually the sequential progression through the successive phases is facilitated by a network of cycling-dependent kinases, transcription factor, and also a protein. Irregularities can lead to abnormal cell proliferation. So this is a fifth-order model, and I would simply like to mention that this is a reduction of a 39 also published model before, a meaningful reduction. It is nonlinear. I'm not going to show you the equations, but I'm going to remind you what I have told you when I presented to you our contribution in log domain with the U and V currents. So in order to tackle this particular problem with some of the best groups working on it, was to actually try and determine what should be the U and V currents in our set so that we realize that. So we were after mapping a whole biological system to a whole electrical system. So what you see there is 24 different variables corresponding to the biological system mapped across electrical variables to the really implementable system. And you can see here how we have determined the particular U and V currents that we needed. Here, 1 micromolar corresponding to 1 nanoampere, and at the same time, we accelerated the biological time. So we can actually do that. We can do this type of real-time computations by accelerating the biological time. This is the circuit, and now you are not going to find anything linear here. All the blocks are the blocks I have shown to you. The multiplication blocks is actually a gain block, like that, and the other thing that we are using is current mirrors. For those of you from technical background, and I know that there are some of you here, you would understand that this is a very risky process to actually do that. So we went ahead, we simulated first, we managed to confirm that actually the particular circuit was capable of implementing the complex dynamics that the model was predicting. So we confirmed quasi-periodicity both in time domain and in phase plane, and chaos both in time domain and in phase plane. But of course, we were interested in periodic oscillations of different chemicals that we had there, concentrations of chemicals. And you can see the mathematics, and you can see realistic simulations with statistically validated models. And these are the phase planes. We had good agreement between all the needed quantities, and we fabricated that. We needed 500 transistors, 2 square millimeters of area, and we consumed only 1 microwatt. So you can do that by actually having, and everything here is in the logarithmic domain, and this is at the forefront of research out there. Voila, we actually managed to replicate the periodic oscillations. We measured that with good agreement. So we managed to show feasibility for something that is very much sought after, both in time domain and in phase domain. Now in phase plane domain. This is one of the first fabricated cytomimetic chips, in certain aspects the first. And recently we went on for a second realization. We focused on the calcium-induced calcium release model of intracellular calcium oscillation, which is actually another oscillatory phenomenon at cellular level. It can be observed in many different types of cells. It has to do with the spatiotemporal organization of cells and so on. It is a second-order model. I'm not going to go through the detail. I will simply tell that we had a compelling, as the reviewers were saying, simulated results that you could see that the biology as expressed by MATLAB was mimicked by circuits as simulated by Cadence. And everything that I have shown to you is published so far. I'm going to show you something that is soon to be published. And this is actually a realization of the CICR model that you see there. These are measured results from this little chip that now consumes a few nanowatts per each of the 16 CICR units that we are using there, only consuming 1.5 square millimeters. All these results I want to mention are measured results which show that it is possible to actually do that. And it is possible to do this type of thing. In some of the special issues we have published, the particular guest editorial was mentioning that these are for cell control, for implantable cell control applications of future medical devices. Where could this lead us? I can see two areas. One is the computational path, where actually you are going to have ultra-low power real-time computation of coupled spatiotemporal biochemical molecular dynamics, which would be able actually to shorten, as we said, the learning cycle for bioresearchers. One can imagine high performance, precise, and fast analog cores reconfigured by a digital periphery so that we have the best of both worlds, so that we have robust systems. One can even imagine variations being purely digital and so on. Would you say that, that this is challenging? Yes, it is challenging. Is it difficult? Yes, it is difficult. Is it impossible? No, it's not impossible. We can borrow ideas from different other fields that have been different other circuits that have been developed before, like this one here, which is for high-performance image processors, where actually they have layers of CNNs, layers of analog VLSI talking to each other, being digitally reconfigurable, and having actually some of the best power efficiencies out there. In my view, this is possible. I'm not going to say to you that it's going to happen tomorrow, but I am going to say to you that it will become, because I would invite you to look at what has happened with the neuromorphic paradigm. Who would imagine 30 years before that we would have the circuits that we have there now? A second area is in conjunction with miniaturized biosensors for synergistic electronic and biological applications. What could those be? I know, for example, that our department pioneered synthetic biology. So you could have, for example, silicon systems that are controllers for synthetic biology. Why? Because actually the silicon system will have much more flexibility as far as the observability and the controllability that you are after. You could also have these type of circuits used for drug testing platforms, fast drug testing, high throughput drug testing platforms, where you can see how and whether the model actually agrees with the biological data. And of course, it could go even for prosthetic or cyber applications, as we have seen before in guest editorials. As I said, this is not going to happen tomorrow. And if you ask me exactly how and why, I would tell you, look, these are the two future directions I see. One is to go for scale processing. People have done something like that, but for the neuromorphic field, for the cytomimetic field, there will be definite adjustments specific to the realizations that we have. But now you have 20 different wafers connected in parallel, digitally reconfigurable, and being able to test hypotheses for neurosciences, systems neuroscience, and so on. This is one way that it can go. The other way that it can go is to go for the ultra-low power chips. Recently, there are chips from IBM and from Intel there that are actually having too many millions of neurons and millions of synapses there that help us test hypotheses when it comes to different neuroscience and neurobiological problems. I think and I believe that these are the two directions forward. This one for the implantable part, the controller part, and this one for the cytoprocessor platform there that will be doing ultra-low power real-time computations. Just out for the record to mention that a 20 centimeter wafer there could actually accommodate more than 10,000 and more, tens of thousands of the cytomimetic circuits that I have been talking to you about. We are at the end. What I have shown to you was how the development of technology, starting from the first transistor, led us to make significant progress in the log domain circuit paradigm. I showed to you how we have improved progressed the field of cochlear implant circuits as an example, as a linear example of the power of our formalism. And I have also shown to you a new class, an emerging class of circuits, the cytomimetic circuits, which again, most probably, our formalism offers the parsimonious solution for the realization of this type of circuits. As Anthony was saying, our research must have, and this is only part of our research. I cannot include everything in one inaugural lecture, but it is clear that there are societal, if you want, implications for both of those parts of the research. So with these thoughts, I would also like to invite particularly our students, whenever they write collector current equals reverse saturation current, exponential VB over VT, that humble exponential there, to always bear in mind that they are doing that only because they stand on the shoulders of giants like Boltzmann, because it is those statistics that give us the concentrations of carriers within those transistors. Acknowledgement time. I would like to thank all the past and present members of my group. Many of them are here, and I'm thankful for that. I would like in particular to thank Dr. Andreas Katsiamis, Dr. Guang Yang, Dr. Kostas Papadimitriou, Dr. Alexandros Hussein, and soon to be Dr. Hamid Soleimani, because I have used parts of their results to present you this. I am proud and honored for all of them to have me as their supervisor. I will continue with George Zafiropoulos, Kostis Petkos, Graham Payton, Simos, Yassin, Momen, newer members, Beksad, Andreas, Ilias Pangalos, Itir, and all the rest. I thank you all for this. Finally, I need to thank my family. I need to thank Pavlina, Agni, and my wife, Georgia. And I have to say in public, and while I am recorded, actually, that if it wasn't for Georgia, I wouldn't be standing in front of you today. So I owe you a lot. And I would also like to thank all the past and present members of our department. I would like to thank my department for giving me the freedom to investigate these avenues, and I would like to thank the college as well for allowing me to also have the freedom to investigate this. After all, we are the Department of Bioengineering. Thank you very much. Okay. Was it okay? That's it.
We are almost finished now. Manos, that was totally fantastic, and I'm sure I will echo what we all think is we learnt a lot. We didn't understand everything. But what we did understand is that you are an academic after our own hearts, actually, and thank you for this wonderful exposition. We have a vote of thanks, and the person giving the vote of thanks is not present here today, but you've already seen his photo on the slides, and I think this vote means a lot to Manos. And so I'll just introduce him. So Douglas Fry is a professor in electrical and computer engineering at Lehigh University. You've already heard he's considered to be the father of log domain field, and through his seminal intellectual contributions, he's received so many millions of accolades. I'm not going to list them. And so it's an honor that he's giving this vote of thanks. So although he's unable to attend here physically, he's he's recorded a short video which we will now listen, and then that will be the end of these proceedings.
Good evening. It is my honor and pleasure to say a few words at the inaugural lecture of my friend and colleague, Professor Drakakis. His resume speaks for itself and explains why he is here. I have known Manos for about 20 years, mainly due to our mutual interest in log domain filtering. I still recall meeting him when my friends, Professors Chris Tumazu and Allison Payne, introduced him as a doctoral student. Not only was I impressed with his obvious enthusiasm, I was also intrigued by his interest in the Bernoulli equation. I knew at that moment that this was an individual that would take things in a new direction. His work in the area has always been of high quality and innovative, two attributes he has manifested well during his career. His special attention to the hyperbolic sign variation of log domain filtering has been of considerable value to the field over the years, as evidenced by his many publications. While I like to think that I have furthered the initial contributions of Sievink and Adams in articulating the log domain paradigm, it is clear that the contributions of Professor Drakakis have significantly furthered my work. And this is in addition to his useful application of the filtering concept to biomedical applications ranging from hearing aids to stem cells. It has been my pleasure to write letters of recommendation from Manos over the years, each time noticing maturity and his contribution to the field. I have been particularly impressed by his commitment to the well-being of his students, manifesting the best of the academic spirit. Professor Drakakis has truly shown himself to be at the forefront of electrical engineering and a benefactor to those with whom he has worked, including myself. I'll conclude by showing my appreciation to another of Britain's treasures, Monty Python. Amongst your vast and diverse weaponry are such things as clarity, enterprise, ruthless efficiency, and a fanatical dedication to everything that makes our profession worthwhile. Congratulations on your promotion, and may you always enjoy your well-deserved success.
That's it.
Wonderful.
Today,